I love talking about chips. I follow the AI silicon market very closely, working with a lot of the major public companies and also a lot of startups. And in this presentation today, we're going to go through a series of what I consider key highlights as part of the industry. First of all, starting off with some definitions. I'm not going to bore you with what AI is and why there's a need for AI. Every 5 slides on every other presentation can do that for you. I'm assuming everybody knows that from here on out. But I will go into a little bit of the technical reasons about why AI works, and then how I see the market as a whole, how it comes together with the different elements of hardware. Following that, I'll go on through to where we are with AI hardware, especially as it focuses on the startups, what startups are winning, what startups have failed, and do a few cases there to go through with you all. And then also I'll highlight a few topics that I've been recently seeing at the IEEE conferences that really make me excited that this is the industry to be in, and this is why we're all here. So to start, I just want to set a baseline when it comes to machine learning and talk about legacy hardware. The usual scale of compute chips runs usually CPU, GPU, FPGA, ASIC, going from programmability to fixed function, with a variety of increasing power efficiency, but decreasing programmability in that. And I'm going to go through at a high level a lot of the hardware right now that most people are familiar with when we're talking about latest generation in these spaces. So to start, I'm going to go with CPU. x86 is still the dominant architecture in CPUs. ARM is following fast. And everybody should know big Intel company is very popular for CPUs, especially when it comes to AI inference. Intel still holds a strong position in AI inference purely running on the CPUs. That's because over the last few generations, they've been included instructions into their CPUs that accelerate machine learning workflows. We're talking about matrix extensions and vector extensions. In each generation, more capability has been added while still remaining the complete programmability of a CPU in that function. The only change over the last I guess 3-4 generations now is the movement to chiplets and how we move high bandwidth data on a CPU around multiple chiplets. So the last few generations of Intel CPUs, we have Intel Xeon is the brand name. We have the 4th generation, Sapphire Rapids, 5th generation, Emerald Rapids. And then we have Intel has split its strategy into high performance cores and high efficiency cores called P and E cores. And we have different families for those currently in the market called Granite Rapids and Sierra Forest. And Intel has also given roadmaps for the future products. But what we're dealing here when we look at Granite Rapids and Sierra Forest is products built on Intel's 3 process node with advanced packaging going up to 500 watts, and in the most extreme case up to 288 cores with Sierra Forest. AMD, similar tack, they went chiplets first. They used a cheaper Global Foundries node for their first generation AMD EPYC CPUs before fully going in on TSMC. They are fully embracing what it means to be a chiplet. You have a small reusable piece of silicon that is cheaper to make because the die size is small, easier to yield, and better to get a higher frequency. And if you compare multiple chiplets together that can all reach high frequency, the idea is you get a better product at the end of the day. They're using more standardized packaging, as you can see in this image here, but they have had 4 or 5 generations now of their EPYC processor line, and this is getting to around 30% market share in data centers today. The latest generation, EPYC 9005, is called Turin, and there's also a version called Turin Dense. Again, they also have 2 types of cores, and here again we're going up, 192 cores and Turin Dense, 384 threads. Lots of DDR5 regular standard memory here, and up to 500 watts. ARM CPUs are taking a hold in the market. The biggest and most popular one is probably NVIDIA Grace. That's going to be part of the Grace Hopper systems and Grace Blackwell systems that's powering many an AI factory this year, next year, and through the rest of the decade. However, ARM, as an IP company, also provides essentially almost complete solutions called CSS. This allows a hyperscaler like a Google, like an AWS, to take a standardized set of core designs, and they can enlist the help of a company like Broadcom to go do the physical design. AWS has an in-house team called Annapurna, and they will build out a custom ARM chip for themselves that will have differentiation that they need. And these are, just like the other CPUs, either used for machine learning management in data centers or for inference. And when you get a copy of these slides, because the slides have way more detail than I'm going to go into about exactly where the generations are and what the latest products are from each company. On the GPU side, Big Green consumes over 90% of the training revenue today. They have released a roadmap out to 2027, with the newest product today being Blackwell. We just had a consumer GPU launch based on the Blackwell architecture, based on the Ada architecture. But what you see here in front of you on the top left is a Grace Blackwell 200. That's a Grace chip with two Blackwell GPUs. And on the right is one of their big 125 kilowatt NVL72 racks, which essentially puts 72 of these GPUs together to act as one. NVIDIA's developed custom networking silicon in order to do this. And you can see by the roadmap on the left, they have a very strong regular cadence where they're also following high bandwidth memory roadmap as well. AMD is going down a similar line, except they're taking more the chiplet strategy from their CPUs. The latest generation product is that one at the top. That's the MI 300X. They just recently launched MI 325X, which is a higher memory capacity design. This is using TSMC and a lot of advanced packaging and HBM to build a high bandwidth, high compute training and inference silicon. The chip on the bottom is the MI250X. That was last generation. AMD's GPUs are currently favored by OpenAI for their inference compute because it works out about 10% cheaper to run over NVIDIA. So these are the sorts of battles that these high-end silicon players are going for in terms of cost per million tokens in their language models. Intel also has an AI product line. They have several chips, and it may get a little confusing as to which chip is delivered to which market, but the purely speaking AI chip is called Intel Gaudi. It comes from an acquisition they made a few years ago of a company called Habana. Gaudi 3 technically launched last year, but is in volume production this year, using a mixture of TSMC 5 nanometer and advanced packaging and HBM2. They also have a HPC chip called Ponte Vecchio. That's the one on the bottom left. And that's using a mixture of Intel's advanced packaging technology. And we'll get to why packaging is important later when you put these chips together. After GPUs, we get to FPGAs. FPGAs have a position in the AI space. It's not necessarily a big position, but it is a dedicated position. As always, FPGAs have always been that dedicated piece of silicon that if you need it, you definitely know you need it. It's got a high barrier to entry, but what the companies are doing, particularly AMD with the Xilinx acquisition, and we'll see in a second with Altera, is they're not just putting traditional FPGA programmable gate arrays into their silicon, they're also including AI engines on that silicon. So dedicated hardened blocks on silicon to help accelerate performance when you need both FPGA and AI workflows. AMD's product lines in this market, it's mostly the Versal product line, though, however, some of the previous product lines under Xilinx, like Vertex, also fall into this space. Intel FPGAs, you may have recently heard that the acquisition Intel made of Altera back in 2015 for 15 billion US dollars, they've recently kind of spun it out again as a subsidiary. So now it's Altera powered by Intel. So Intel still owns a controlling stake. However, it's no longer 100%. And that's fine. That's formalized over Q1 this year. We should hear more about it soon. But their latest generation product line is called the Agilex. FPGA is built on Intel process technology. And their value add here, alongside a lot of the AI silicon, is the fact that they offer customization with other Intel IP, particularly transceivers, particularly SerDes connectivity. And they're rolling out their Agilex 3, 5, 7, 9 product lines pretty much all in volume by middle of the year. Some of them have been slow to roll out, but that was due to the acquisition back in 2015. On the ASIC side, so this is dedicated silicon. I want to highlight a couple of things here that exist in the market, but then we'll go into what the AI startups are doing. Smart NICs, so this is network controllers with intelligence in them. There is a spectrum here. So in these data centers, especially in AI data centers, it's not just simply enough to have a routing table and send a packet of data across a network. You will need to be smart about load balancing, where it's going, maybe even doing some compute along the way, or doing things like asynchronous or reduce. And you need the switches and you need the network cards to know how to do that. As a result, we have a continuum of smart NICs, anything from the traditional foundational network controllers to offload engines, so you get some of your performance back from your CPU or GPU, through to DPUs, which have advanced capabilities, usually security, especially in multi-user tenancy AI clusters, all through to exotic FPGA-based smart NICs. Now, this isn't an AI chip, but I just wanted to highlight D.E. Shaw's Anton 3. For those who don't know who D.E. Shaw is, it is a research group in New York run by a hedge fund manager. He made his billions, and now he just writes research papers for the sake of improving molecular dynamics simulation. They have created a dedicated chip just for that, called Anton. They're currently on their 3rd generation, and their chip allows them to perform 100x better than the world's fastest supercomputer, all because they took the time to build a dedicated chip specifically for their exact workload. Programmability is obviously not as big as a GPU because it's a dedicated ASIC, but it does enough for what they need it to do. And like I say, they're on the 3rd generation, and as a result, they are able to put tons of papers into their field simply because nobody else has access to this hardware, and it gives them an advantage, even though it's not necessarily an investment or a financial one. So those were traditional legacy hardware that hopefully most of you will know, just bringing everybody up to speed on what the latest product names are. I want to go over some of the perhaps non-von Neumann architectures that are making it their way into AI that are worth talking about. I've listed this as old and new because a lot of these techniques are old. We used to do them 30, 40 years ago, and now they're becoming good because people actually have silicon resources to make them work, or at least try to. First one here is analog computing. As we all know, digital is limited in the numbers it can present. So why not use an analog wave? And then you can do things like multiply, accumulates a lot easier using the voltage of resistors across an array, or in terms of one startup on this list, actually doing Q equals CV rather than V equals IR. It offers promise because this is a very low power and low latency technique if you just let the physics do the math rather than trying to force it through regular digital compute. It also means that the accuracy level of the AI algorithm is semi-independent as opposed to digital, where we're dealing with floating point formats. The problem, however, is that you still need to convert to the digital domain for anything to be readable. These analog devices are hard to manufacture reproducibly, so you may have variance in the manufacturing, and that leads to scaling issues. As a result, typically these sorts of chips have ended up more in the edge and embedded markets and not into, say, the data center markets. We'll get into that in a second. But there are several key players here, especially IBM. I work with them, and they're pushing forward for a lot of this analog computing stuff. The neuromorphic computing, again, this is super, super, super old. This is the original, let's take what the brain does and see if we can make it computational. By doing spiking neural networks. So can we respond in the time domain instead? This has, again, been around for decades. except that now with the advent of machine learning, we're able to do a lot more with these algorithms when we put them into silicon. The most famous spiking neural network silicon is probably Spinnaker. They're actually running simulations on Spinnaker 2. I believe that's all in Manchester University. And the whole point here is that it's so scalable. You can have millions and billions of neurons. I believe the original design of Spinnaker 1 was to fit a mouse brain into one, megawatt supercomputer. However, some of the latest chips actually come out of companies like Intel. Intel launched their Loihi 2 chip built on the Intel 4 process. This is a digital neuromorphic chip. So it's relying on traditional digital cores, but designed in a way to handle spiking networks. The second generation chip solved a lot of deficiencies in the first. This, however, is still very much a research project, part of Intel Labs, and they don't have any real plans to productize it yet, but they do work with universities and governments and such to develop the infrastructure around neuromorphic computing. I spoke to the CEO a few weeks ago of this project, the lead of this project, and he's still really excited, and he's been there 12, 15 years, and he can't get enough because everything's just taking off for him. Quantum computing is also, the other one that's been around and everybody's waiting to see, will it, won't it? Is it 5 years away? Is it 10 years away? We're hearing more and more about how quantum computing can be useful. I'm sure many of you saw the Google Willow announcement a few weeks ago for their 105 qubit chip, able, as they were scaling their qubits up to reduce quantum noise and quantum error with their design. They demonstrated it with a really bad benchmark, and I could spend an hour complaining about that. But they still are pushing this industry forward, and people are already making money on quantum computing. You can go get quantum resources in the cloud now. Spot pricing from IBM's partners right now, I think, is $2.40 a second, if you're interested. That's coming down, though. Three main areas quantum computing is focused on right now: physics, chemistry, biology, so the physical world. We have mathematics and encryption, so the typical Shor's algorithm, traveling salesman type problems. And of course, we have to put machine learning in there. The only problem is it doesn't really apply to much else. There's a high barrier to entry. And we're still in this issue of quantum error. What do quantum results really mean? IBM and partners, I actually did a video with them a couple of years ago that's sitting at about 500,000 views on YouTube right now, if you want to go find out about what they're doing. Their recent roadmap is talking about going to 10,000 qubits, 100 million gates, and they have over 1,000 research papers out in the field with calculations based on their quantum machines. So it's coming. It's coming. The question is scale and whether these type of qubits are the ones that are going to win. Again, we could spend an hour talking about different types of qubits. Another function, another potential is optical computing. Why bother with electrons when we can use light and be smart about how light works using interferometers to do calculations? The benefit of optical is just simply no power and speed of light fast. So if you can build a chip, it almost doesn't matter how big the chip is as long as it works. The problem is it scales poorly. If any of you are familiar with this part of the industry, a lot of work is going into simply how do we make an adder in the optical domain? How do we make a multiplier? How do we get a read in, read out? Part of the problems here is also manufacturing. As a result, a number of the optical compute companies, especially, I mentioned two here, Light Matter and Lightelligence, both of them have essentially pivoted to optical networking. And we'll get into that in a second because optical compute is still really hard. So there's a look at some of the interesting architectures that are going on, simply just non-von Neumann. I could go into things like data flow architecture, CGRA, systolic array, but we'll cover that in some of what's coming up. But I do want to talk a little bit about reduced precision and why there's this drive to talking about FP16, FP8, and why having fewer bits to represent your numbers matter. Today, high performance compute, if we're doing physics simulations, is all done in 64-bit floating point. This gives the researcher the widest range of numbers to use and incredible accuracy. So if you're modeling Concorde, you're modeling an aeroplane going at multiple thousand kilometers an hour, you need high accuracy and you need high range to be able to do those calculations. The thing is, with machine learning, we're dealing with a lot of small calculations, and it's often described as fuzzy mathematics. So perhaps in order to showcase whether something is between 0 and 1, we don't need all the billions, trillions, quadrillions of points in that spectrum to be able to represent our numbers. As a result, we go down reduced precision. Here on this graph, I'm showing you the difference between FP32, which is a 32-bit representation, FP16. This is how many bits are assigned to different parts of how the number is calculated in the computer. But the important numbers are here on the right. You can see that the range is considerably worse and the accuracy is considerably worse. But if your algorithm can handle that, you're suddenly using less power and potentially doing more compute in the same area, and doubling your compute as a result. And power is really where it's at. If you can maintain the accuracy of your calculation, power is a godsend. It really is what makes this work. Based on numbers coming out of ISSCC, the amount of compute you can do with an 8-bit number, so FP8 here at the top, you can do 33x the compute in FP8 than you could do with a full FP64 double precision HPC code. So we're talking about building AI factories with megawatts and megawatts of capacity. Well, if you can do 33x more compute and your algorithm can withstand the reduction in range and accuracy, then you've just reduced your costs by 97%. So this is why we do it. And here's a representation of a few of the numbers that exist in the market. Again, we could speak about which ones make sense for training, which ones make sense for inference. Towards the bottom here, there's this new set of formats called block float formats. Microsoft did a good paper. They weren't the first, but they did a great paper about that 4 years ago. NVIDIA are now adopting it. AMD are now adopting it. Other companies like Tenstorrent are adopting it, but it's the way forward. So from that, I do want to talk about the silicon market. I mean, I've gone through a number of companies. I've gone through a number of different architectures and why we're doing it. I do want to speak about how I separate the market in my mind as to what company does what and what hardware does what. I separate the market into 4 different battlegrounds, and I'll take you through, starting with the top left. And I think most of this should be obvious to anyone who's used any machine learning here. At the top left, we have data center training. This is your big fixed workload. This is building your foundation model with lots and lots of data, needing lots of compute. This is why OpenAI needs hundreds of thousands of GPUs. This is why people are building data centers with massive amounts of megawatts capacity. This is why people like Elon Musk are bringing in cooling trucks and power trucks rather than waiting for power stations to be built so he can build his data center. So we have large clusters of chips working together, typically on one problem or a subset of problems. The software is evolving faster than the hardware. And here we develop what are called foundation models. So these are the high-level models that then get fine-tuned down into more digestible inference chunks. On the top right, we have data center inference. So while we have data center training, we also have data center inference. So this is when you are doing your shopping online, or a company is dissecting a bunch of health data to make sure you're getting the right treatment or the logistics are done in the right way. This is typically large amounts of clusters of PCIe cards. So PCIe card. Hopefully, I'm not saying anything new to anybody here. And these will sit in lots in data center racks, typically running independent workloads, or you may have a few of these chips working together, but they're running on inference. When you train the model, you then have to run it in inference mode in order to get your result. The thing is that workload is lumpy. For example, if you're doing something that directly correlates to what a user is doing, you may find out that between the hours of 9 a.m. and 5 p.m. or 6 p.m., your workload is a lot higher than at 3 a.m. So you're going to have a lumpy workload, but this is typically absorbed by a cloud business model. But we will have companies in both training or inference typically. On the bottom left is arguably one of the newer areas that I think is worth highlighting, and that's localized inference. So this is when a company needs data center inference like performance and power efficiency, but they don't need it in the cloud. They need it local. We're talking edge servers. So this may be a set of GPUs in your retail store, in your gas station, or in the office that is responding to help desk requests from your company of 50 users, for example. As a result, you're dealing with a lot of in-network requests during office hours. You're not dealing with hundreds of thousands of potential users using APIs over the cloud. And it's arguably just a downsized version of data center inference. The fourth one is almost completely separate from the other three, and that's edge inference. What I'm talking about here is the AI that your smartphone or your PC or your smartwatch or your home thermostat might be doing locally on device. It may be doing something simple as presence detection or keyword spotting. This is very small custom microcontrollers or ASICs, usually built by the typical IoT and embedded companies for things like wearables, XR. It's the traditional IoT market, essentially. And these edge inference aren't running the big GPT models. They're running super small models, typically designed for one purpose. Like I said, presence detection or keyword spotting. Very specific markets, but as edge tends to do, these chips tend to stay in circulation a long time when they're very effective. And in terms of companies and chips that are in these spaces, I've got a lot of names of companies here. Hopefully you'll recognize a few. A number of them are startups, but data center training is the hardest to get into because it requires lots of big compute chips networked together with lots of high bandwidth memory. There's a high cost entry to even build the silicon, but then there's a high cost entry to get people to use the silicon. This is why NVIDIA, with things like CUDA, have been able to accelerate to where they are today, because they planted the seeds for this 15 years ago. My claim to fame is I took the first CUDA course outside the US back in 2009. Not for AI, it was for HPC, but the sentiment still stands. If you can get hardware in the hands of users early, you can build up a base. NVIDIA and AMD are typically the main players when we talk about data center training, but a couple of the startups also play in the space, the two big ones being Samba Nova and Cerebras. We then also have data center inference. So again, think of all your PCIe card players. So this NVIDIA does specific data center inference cards, or you could use the big ones as well. AMD has the MI210, but the 300X is also popular, Intel's Gaudi 3. This is where we see things like Google's TPU, Tenstorrent and Groq and IBM and a bunch of other startups playing the space. Localized inference often take a set of the DCI players, the top right players. But recently, for example, Qualcomm just announced localized inference boxes with their partners, specifically for things like in retail inference. And then we have the edge inference players. Like I say, these are typically the small chip companies. They're going to very specific devices like smartwatches and IoT. So in terms of startup funding, if you spend most of your time in software, you'll be thinking of tens of billions of dollars that play in the software space. Hardware isn't that much, but it's still quite significant. I track around 150 or so of these hardware startups. These are companies completely globally, plenty in Asia, plenty in Europe, plenty in the US. But I've been tracking them for a few years now, and the number of startups that exist have only gone up. And this leads to two questions that I keep getting, which I've highlighted here. One, are any of these startups going to merge and come together? And one or two of them have. Are they going to fail? Again, one or two of them have. Or are they actually going to IPO? Are they going to exit? Are they going to do what traditional startups are meant to do? Either make money or be acquired. It's a slow market. people have been waiting for this for 5 years, but the level of interest has been pretty good. 2024 was actually a serious year for reducing the number of startups, and I've listed 6 here. And arguably, there's not 6; it's really like 5. There's one company that announced that they're going to IPO. That's not fully filed, but we'll get into that. There have been 2 acquisitions, a merger, and a couple of deaths. And we'll get into that. One of them's not really dead. But in total, just in 2024, I tracked over $3 billion of funding raised, which isn't insignificant. People were saying almost post-pandemic, oh, there's no more money in AI hardware. Nobody's being able to raise any money. Turns out VC funds are opening their wallets again. And in certain circumstances, quite a lot. 10 companies I track raised over $100 million. That's a good 9 figures. And in total, I track about $17 billion in this market. So yeah, in 2024, we had 21 companies with funding rounds. And I've listed the top 10 on the right here. So this is companies related, either doing AI hardware specifically or related to AI hardware. And a few of these names, I'm sure some of you will recognize. Companies like Tenstorrent, Groq, Light Matter, I mentioned before on the optical side, IR's on the optical side. AI is on the edge inference side. And then we have a few others. There's some serious investment going on still. Some of these are Series D, some of these are Series C. There's still a bunch going into Series A and Series B as well. And this is one of my big graphs, and I apologize if it's not coming through in full resolution. Hopefully, if you can't see it, we'll get the slides. But this is just every company I track, that has, as a total, raised over 100 million US. And I've put what's happened to a few of them on the left-hand side. Then this is the other graph with the sub $100 million as well, just to show it off. For this graph, I've just limited it to like the top 15 or so to make it a little bit easier to read. Right at the top there, you'll see Horizon Robotics, which is obviously a Chinese-based company that deals in smart city. Being in the West, I don't hear much about them, so I actually don't have much of an insight. They haven't raised much money, at least publicly. These are all what I've discerned publicly. If they've raised money in private, unfortunately, I don't have those numbers. But we do have 3 companies in the US who have raised over $1 billion, and another 7 who have raised over 500 million. So who's hot right now? Which companies are worth keeping tabs on to see where they are in the market? The first one here is Tenstorrent. And full disclosure, this is a company I work with, helping them with their messaging. They were founded in 2015 and they've raised over $1 billion. The current CEO is this guy on the right, who hopefully a few of you will recognize is Jim Keller. He's pretty famous for being ex-AMD, Tesla, Intel, Apple, and waving his magic wand everywhere, and everything he seems to touch turns to gold. So now he's at an AI startup that he actually provided the seed funding for, but took over as CEO a couple of years ago now. And they're going through a productization cycle on their 3rd and 4th generation products. As a company, they have 2 major product lines, which is a bit different to most other companies you'll hear. Most other companies that I talk about only deal in one thing, and that's an AI chip or AI IP. What Tenstorrent is doing here is they have both AI IP, which is called the Tensix, but they also have a high-performance RISC-V core. So not only are they going after the AI market, they're also going after the CPU market. And they're finding out that when a company approaches them to speak about one, invariably the conversation often goes towards the other. So they will sell licensable IP. That's a big part of their product offering. But they are offering chiplets to full servers. So from PCIe cards. I actually have a couple up here of their 3rd generation product. They've already done major deals with LG, Hyundai, Samsung. I believe all 3 of those are also investors. They're also working very closely with Rapidus. And Rapidus, if you don't know, is the Japanese effort to restart high-end manufacturing, leading-edge manufacturing in Japan with a 2-nanometer fab that I think just got its first EUV machine delivered and should be producing wafers next year. They're working very closely with them to develop an AI chiplet for the Japanese market. The beauty of Tenstorrent, unlike a lot of other companies you'll read, is that you can go buy their cards now. It's almost as simple as Amazon Buy It Now. You can go to their website, and for $1,000, you can get their 150-watt card, and it will be delivered to your door within a week or two. A lot of other companies don't do that, but this is because Tenstorrent believes very heavily in things like open source. So as a result, they've sold thousands of these cards already since they offered them last year. They've had over 5 to 10,000 developers who are already building on their cards, but they're even producing research papers that Tenstorrent themselves don't even know. A number of companies on that list won't work with anybody unless they have direct knowledge of what they're doing so they can micromanage. Tenstorrent's the other way. It's a case of send it out into the wild. Philosophy being that if there's an error, we want to fix it. If you're being very tightly controlled with your hardware and there's an error that you don't spot for 3 generations and it comes to bite you, that's on you. Tenstorrent wants to go the other way around. And they're selling servers, which is down on the bottom right with 32 of these cards in. Groq is also big name in the business. They get a lot of press, and that's because they have a very enthusiastic marketing team. Kudos to them. Again, founding in 2016, again raised just over $1 billion. Their CEO is Jonathan Ross, who's ex-Google, ex-TPU. So I'm sure you're aware of all the popularity of Google's TPU for inside Google use. Jonathan Ross is part of the team that developed the first TPUs. Their product is called the Groq LPU, Language Processing Unit, a data flow chip. Their business model has changed over time because this is an old chip built on global foundries that wasn't initially built for language. However, it is of an architecture where they are competing for the fastest chips on the market. Unfortunately, you do need 10 racks. It's very power hungry. Their company will live or die based on their second generation chip being built at Samsung 4 nanometer. That should be taping out towards the end of this year. Their main problem was more of a onboard memory, not enough of it. So the second chip essentially will address that. Third company on the Who's Hot is Cerebras. This is the largest chip in the industry. Normally, when we speak about chips, we speak about 100 or 200 square millimeters in that range for things like smartphone and desktop and laptop. Big data center chips, we speak about 600, 700, 800 square millimeters. That's like the physical limitation that you can print inside the fab. They developed technology where you can cross reticle stitch chips together. As a result, they can make a chip as big as a wafer. And as a result, you essentially increase your memory bandwidth as long as you can put your model on a chip. And it can do things that other ASICs can't do simply because of its size. The full chip, it will run a full algorithm. They implement redundancy, so they have a near 100% yield as well, but it is a custom solution with custom cooling. Their latest generation is the Wavescale Engine 3, which is the chip you see here in the system on the right. Each one of these costs around a couple million. It fits in a standard 1314U of a standard 19-inch rack, but it has 900,000 cores built on TSMC N5, has 21 petabytes a second of bandwidth to the SRAM. And compared to what NVIDIA offers, it's just orders of magnitude above. The main criticism is the capacity, and that's obviously being worked on. But this company is the only AI hardware startup to date that's in that sort of top list of chip that I gave on the previous slides. That's actually made more money than they've raised. They've made $1 billion from one sale to one customer in the Middle East. And then right now, this is the company that's going through IPO. So definitely worth keeping tabs on what they're doing. Now I'm going to go into a couple of failures. And we're just getting into the last few slides here. There have been a couple of major failed companies or companies that have exited in less than stellar circumstances. And the big one was Graphcore. This was heralded as a key component of the British industry, me being British. So again, another 2016 company. They raised almost $700 million. Their main problem is that their chip, when they first came out with their chips, They were great for the computer vision AI models at the time, but they did not do language models. They didn't do transformers at all. And they came unstuck because rather than building a transformer enabled chip, they decided to double down with the chip they had and be a lead partner for custom packaging with TSMC. This is the Bow IPU on the right hand side, this wafer on wafer processor. Great technology, improved performance 30%, for only a small increase in cost by putting the power delivery on a second chip and stacking them. However, because it couldn't do language models, nobody really wanted it. They actually lost large deals with Microsoft and Dell that were initially in the pipe before Transformers came out. Their roadmap included a 3 nanometer chip built with TSMC, but unfortunately, right now that was meant to come out beginning of 24, or even end of 23. We still don't have large 3 nanometer chips from TSMC of sort of like the 600 square mil. So they ran out of money. SoftBank acquired them middle of last year, but they technically still run independently and they're getting investment, and nobody's really quite sure what they're doing. The other what happened to is Mythic AI. If you're familiar with any of the analog compute chips in this industry, this is perhaps one of the biggest sort of failures. Founded in 2012, raised $170 million, died in 2022 just due to they ran out of money. They had a analog computing memory solution that was good for embedded, and they were aiming to get it into data center inference. But as I said before, analog is hard to scale in manufacturing, but also because it wasn't transformer based and it was kind of edge. The products you see here are M.2 modules, and these are the sorts of things that would go into your notebook, not into the data center. They had interest from Lockheed Martin and defense contractors, but simply they burnt out, didn't raise enough, and spent too much money. They did get a small cash injection in 2023 of about $11 million. And since then, the only news we've heard of them is that they've changed CEO twice. So who knows what's going on. And then I want to just quickly finish on some topics that's dominating what I'm seeing at conferences. The first one is advanced packaging. This is how we stack chips together. You may have heard of 2D, 2.5D, 3D. I recently did a panel with Applied Materials IEDM about what's coming after 3D. Is that 4D or is that something else? And so as a result, we've got a lot of technologies here, as you see on the left, to do with how do we go beyond the basic limits of what a fab can build in terms of, how many square millimeters. Things like co-packaged chiplets, silicon bridges, 3D stacking, whether that's logic on SRAM, SRAM on logic, or the holy grail, logic on logic. We've got HBM4 coming in the future, which is another area of customization in packaging. And then in the future, optical waveguides, heterogeneous integration, how small can we make the bump pitch of these stacked parts, and then glass substrates is like the 2030 product to look forward to. TSMC, Intel, Samsung all have product names for this. You may have heard of CoWoS, EMIB, Foveros. I've got a couple of slides here just showing those, but there are also other suppliers of packaging, traditionally called OSATs, and supply chain enablement. A few companies here that are worth tracking, and then there's the research arm. This is one slide from TSMC's OIP event that they held in September last year, just showing that you may recognize the chip, how it looks on the slide. Looks like a lot like the chips that we saw before. Turns out there's a roadmap for this, supporting how big can we make the chip, how much memory can we put into it, and what process nodes we can support. TSMC say they've got over 150 customer product tape outs using this technology, and that will go skyrocket right now. Their main limitation is they actually don't have enough capacity to manufacture this, and that's what's limiting NVIDIA from selling more. Intel is the other advanced packaging player in the market that people talk about more frequently. They have this connectivity called EMIB, Embedded Multi-Die Interconnect Bridge. This is essentially an embedded silicon interposer technology. And the goal here is you don't need a big silicon interposer. Why not just use a small one that's embedded into the chip? Their stacking technology is called Foveros, and that's going through multiple generations as they bring the pitch down and can get higher density interconnects, but also stacking more and more. And they're the company that's spoken most about glass core substrates, which, as I mentioned, is that sort of 2030. We start replacing the traditional PCB in chips with a glass substrate, which can be better manufactured to deal with high frequency signaling like 400 gig SerDes and beyond. The next topic that's dominating conferences for me is connectivity. So if you're familiar with how a standard AI build-out works, you have two types of connectivity. Inside the server, you have all the chips connected together. So that's between the GPUs, and there are standards around this. The one most people most familiar is NVLink from NVIDIA. We also have UA-Link, which is an industry standard that mostly everybody else is using. Sometimes companies use Ethernet for chip-to-chip connectivity. Tenstorrent is doing that with their, or they will have a custom design, and that's what Google does with its TPUs. But that's inside the server. You also have outside the server. How does it connect to the rest of the data center? How does it connect to other servers that may look similar to, and how does that scale the workload? The traditional ones here are Ethernet and InfiniBand. InfiniBand, made by Mellanox, was acquired by NVIDIA a few years ago. OmniPath is making a return through a company called Cornelis Networks, and then there are a series of custom operations here. But we have the Ultra Ethernet Consortium, as you can see on the slide, and the UA-Link, Ultra Accelerator Link. Funnily enough, both being championed by AMD and then eventually both being championed by Intel, because it turns out there's a big green monster in the room that everybody needs to fight against. But it showcases that you do need high-speed SerDes IP on leading-edge process node technologies in order to be competitive in the space. And finally, the last thing is co-packaged optics. This is something I'm really interested in. Normally, people are familiar with optics in the data center of being, how do we get from one server, one side of the data center to the other through switches? Inside the rack, we have copper, but outside the rack, between switches, we probably have electrical. Co-packaged optics is different. This is how we connect two chips together rather than two servers together. So this falls under different names. Silicon photonics or integrated silicon photonics is what most people know it as from academic and research. Broadcom and Marvell call it co-packaged optics, and startups like IR Labs call it optical I/O. I have a feeling the industry will coalesce around co-packaged optics. But simply here, the limitation is that you can only do so much with electrical. It's power hungry. There is actually a theoretical bandwidth limit, and it looks like 1.6 terabit per second maybe in that realm. But also, when you connect multiple GPUs together in an AI system, right now 8 is the norm. NVIDIA has their NVL72, which is 72 chips acting as one. However, they have to have custom electrical switching and active cables. And as a result, they'll tell you that NVL72 is around 300,000 components, of which they all have to enable the supply chain for. So why not just build an optical chiplet into your GPU, into your ASIC, and connect them that way? Multiple benefits here. One of the companies that I work with is called IR Labs. This is an example here where they've embedded it into an Intel FPGA. And they've been able to demonstrate 4 terabit per second chip-to-chip bandwidth over optical connectivity. They also build the light source, and it's incredibly power efficient compared to Ethernet, for example. This is a mock-up of what they would expect to happen in the next few years. You have an ASIC in the middle with HBM on the side, and then 10 optical chiplets connected on the other shoreline. And the whole point here is these can either be connected to other AI chiplets or other AI chips, or they can be connected to things like other HBM. And then you end up with a tiered memory solution, but still a lot of fast memory. NVIDIA's heavily involved in this. NVIDIA showed this slide at IEDM in December last year, showing off the second layer from the bottom here, showing photonics with 4 chips and 12 optical chiplets connected. So NVIDIA is definitely going down this route. This is a little bit of a different situation. This is a company called Lightmatter. They showed this at Supercomputing. Instead, they're doing off-chip optics, but instead of having a chiplet, they have a full interposer. So in this case, they said this is a customer product with 8 compute chiplets and a fully unified optical base layer, optical optical interposer that not only allows the chips to connect to talk to each other very fast with super low latency speed of light, but also they can connect out to lots of other chips with this product. I expect to hear more about this during 25, but this is again one of the startups that I mentioned. And this is important, right? It seems like everybody is investing in all of these solutions because at some point optical is going to be here. Between IR Labs and Light Matter, two of the companies I listed here, they've raised 555 million in 2024. IR, they're both Series D. IR raised money from AMD, NVIDIA, Intel, Global Foundries, and the defense sector. Light Matter from Google, and that was a pretty big investment. And they also have investment funds backing that as well. This is all expected to be delivered somewhere between 26 and 29. Companies like Broadcom and Marvell and NVIDIA and Intel and AMD also have internal projects. People are putting eggs in every single basket because whatever wins is going to be super important. The problem right now with optical is things like you have to design it with your ASIC from day one in order to get it to work. If you've got fibers attached and you want to be able to reattach, you have to do that with accuracy and repeatability. These things are often subject to thermal variance, so you have to find a way to narrow that down. Like analog manufacturing, the variation in manufacturing is something that takes time to sort out, but also volume. You're not going to get an NVIDIA contract if you can't do at least a million chiplets a quarter, for example, or a month. Right now, we're kind of in the sort of 10,000 a quarter. So that has to ramp up and scale with either photonics processes or packaging processes. But then on top of that, we also have software stack to deal with. And this is the last slide. And I kind of want to showcase why this matters for optics. And I'll take you through. What we have on the left here is an example of what a modern AI chip looks like in 2024. You have an ASIC compute in the middle with about 8 high bandwidth memory chips around the outside, and that's how you enable your compute. Your next layer of connectivity is to the GPUs in the system, and this is often an 8-way system. And then on top of that, you have your Ethernet, your InfiniBand, which at the high end is an 800 gig network today. As we go to 2026, starting at the bottom, we expect to go from 8 HBMs to 12 HBMs. So you're adding 50% of your memory bandwidth and capacity. We're going to higher stacks as well. But you're only adding 50% to that. At the top on the networking, we're going from 800 gigabit per second to 1.6 terabit per second. So we're doubling the high level network. But in the middle, if we get optics to work, instead of having 8-way GPUs, we be able to have 64, 128, 256-way. If you traditional workload will have memory bandwidth limits. If you can consume most of that memory bandwidth requirement without needing to go to your Ethernet, that speeds up your workload. That reduces your costs to make tokens. I said here, there's a paragraph here. Today's GPUs in training rarely go beyond 35 to 40% utilization, or you can do some software tricks to improve that. But most of your GPU sits idle because you're waiting on memory, you're waiting on synchronization, you're waiting on bandwidth between systems and GPUs. If you can get that up even 5%, you're saving millions of dollars. Millions, especially if you're in a foundation model. Even when you're talking about inference models, if we're talking about OpenAI, this is incredibly important for ChatGPT and DeepSeek and similar things along that path. And I said at the bottom here, not only can you connect chips together, but you can just increase the HBM. So instead of having 8 going up to 12, imagine you had 8 going up to 100. And then instead of having a 1024-way GPU system, you only had a 16 or a 32-way GPU system. There's a trade-off there. But this is what optics will hopefully enable when it gets to the market. And I'm really excited that this is an area we should focus on alongside packaging, connectivity, and everything else. And with that, I'd like to thank you all for listening. Again, as you probably tell, I could speak about this for hours, and I regularly do on my YouTube channel if you're that way inclined. But yes, thank you.